Okay, so today we are designing an half-bridge inverter. This is the circuit topology. We've got a split DC bus. In this example, we are assuming that this midpoint reference is held by two independent voltage sources that split the DC bus exactly in half. In a real design, we would have two real capacitors, but for this example we are assuming the capacitors large enough to neglect the DC voltage ripple, the DC bus ripple. Then we've got two switches that share a common switching node. This node feeds directly to the output filter, and then we will study this circuit with a purely resistive load. Let's start by the drive signal of the two switches, for which we are using the sinusoidal PWM modulation, and we've got the top signal and the bottom signal. When switch 1 is on, switch 2 will be off, and vice versa. It's important to note that these two switches cannot be on at the same time, otherwise we are shorting directly the source, and this will be destructive for the circuit. So to drive these two switches, we've got to have a sine reference voltage that will be the output waveform that we want on our load, and a triangular carrier wave at the switching frequency. So to make this signal in LTspice, we need a voltage independent source to generate the reference, and this is a sine with our output voltage in root mean square for the amplitude, and the output frequency for the frequency of the waveform. And then we've got our carrier wave, which goes from minus AC stands for the carrier amplitude to plus the carrier amplitude. So this carrier wave is bipolar. We've got a rise time of half the switching period, because the switching period is just 1 over the switching frequency, and a fall time of also half the switching period, and as a period 1 over the switching frequency. So to drive the switches we need two signals, which are gate top and gate bottom. And for the gate top, we can say that the switch 1 will be on if the reference is higher than the carrier. So if reference is higher or equal to the carrier, we've got 15 volts to drive the switch on, else we've got 0. And the other one is just the gate top through a NOT gate, basically. And we've got if the reference voltage is less than the voltage than the carrier voltage, we'll have the bottom switch on, else we've got the bottom switch off. Okay, so that's it for the sinusoidal PWM. Let's define some values before approaching the sizing of the output filter. And for this inverter, we would like to have a sine wave at the output of 220 volts of root mean square, and a peak value of 311 volts with an output frequency of 50 ohms. This is the model of the switch. This is just an ideal switch for this example. We've got a purely resistive load of 50 ohms, and in this case we will have an output power of 1 kilowatt. It's important to define a parameter, which is the modulation index in an inverter, which is the ratio between the peak voltage at the output over the carrier amplitude. We want to work in a linear operation of this inverter, so output and input are related linearly. And in this operation, the modulation index can be just from 0 to 1. So in this case, we want the inverter to operate at a 0.8 modulation index. And with this value, we can find easily the carrier amplitude that we need. So let me do the calculations, and I will add the parameters, and I will add also the switching frequency, which for this inverter will be 5000 Hz, so 5 kHz. So we've got a dot param of switching frequency 5K. And then AC amplitude of our carrier of 389 volts. So these are the parameters. Okay, so we have defined these parameters, and one important fundamental parameter that is missing, of course, is the VD parameter, so the DC bus value. It's important to note that you can't choose independently the peak output voltage and the input voltage, because they are related in an half-bridge inverter with the modulation index by a simple equation which says that the peak output voltage is equal to the modulation index times the DC bus voltage over 2. So by inverting the equation, and by knowing that the modulation index is just the ratio of the peak value of the output voltage and the carrier amplitude, we can know what voltage to have at the input to have a desired output voltage. And in this case, we will need a output voltage rounded up at 800 volts. So these are all the parameters that we need for the two sides the bridge, and now it's very important to select properly the cutoff frequency of the output filter in relation, of course, of the switching frequency and of the harmonics of the inverter. So for an inverter, this is a general rule that the first cluster of harmonics is always in the proximity of the switching frequency. So the first cluster of harmonics will be, in this case, at 5 kHz. So we need a low pass filter that is that has a frequency which is much less than the one of the switching frequency. And for a general rule of thumb is to select a cutoff frequency of the filter less than a tenth of the switching frequency. So in this case, less than 500 Hz. And for this example, we want to have a low pass filter with a cutoff frequency of about 400 Hz. So let me add also this parameter. This is the cutoff frequency of our filter, and then let me open the notes so I can explain you better the process to design the output filter. So these are the two relations that we discussed earlier. The cutoff frequency is given by this formula, and we are going to use to design the filter because another factor, we need another equation because we have two unknowns here and only one equation, which is the one of the cutoff frequency. So we need another equation which we can get easily by considering the Q factor of the filter, which is just the resistance times 1 over the characteristic impedance of the LC circuit, which is the square root of C over L. So the Q factor is very important for filter design. Also in antennas is a value which is very common in the electrical engineering world. And in this case, for our RLC circuit parallel, we can say that the more is the resistance, the higher is the Q factor. And the higher is the Q factor, the more energy is exchanged through L and C. So basically this factor tells us how well our filter resonates. And of course we don't want the filter to resonate too much because the energy gets trapped in the LC tank. And an intuitive explanation of why this filter is this factor is proportional to the resistance can be looked directly to the circuit, and we can see what if the resistance is high, so the load is absorbing less current. So if we find ourselves in the situation of light load, the LC tank is resonating a lot because not much current and energy can pass through the resistor. So we want to work, of course, at high loads, so a lot of current has to get absorbed by the resistor, and this is important that we want a low Q for an output filter, and a value that we can assume is just 0.7 for Q. So I'm going to write this just for reference. We won't need it in LTspice, but I want to write it here to have it as a reminder. So we fix Q to be 0.7, and then by knowing this we can we know Q, we know the cutoff frequency, and with the solving this simple system of two unknowns and two equations, we can find the inductance and capacitance value. So doing the calculations and some rounding up the numbers, we can say that L1 is 28 sort of microhenry and C1 is 6 microfarads. Okay. So we've got basically anything to run the simulation. We've got the output filter sorted by the means of the Q factor. So we now with this technique we can just design any output filter for any inverter, and we do not have to guess the values of the output filter by just looking at the order of magnitude basically of the input voltage or the output voltage. We've got the cutoff frequency of our filter, which is, here I missed, is 400 Hz. We've got our switching frequency of 5 kHz, modulation index is 0.8, our load is 50 ohms. We have our output voltage parameters and our carrier amplitude. So we can run the simulation with a transient directive. And so let's see if everything works. Okay, so I made a mistake for the capacitor value. It's just 6 millifarads, not microfarads. And this is the output voltage waveform. We can zoom in and we can say that the peak-to-peak value is 460, so it's about right, let's say. And then we can see the ripple. We can see a transient here, which is and also the Q factor is impacting also on the transient. The more the overshoot, the more is the Q factor. So that's it for this design video. I hope everything is clear. If not, let me know in the comment section. Let me know if you like this kind of design video where I just show you the circuit and how to find proper values. And for the next video of this inverter series, I would like to stress more the filter output design and also consider just a load that is ohmic inductive with so not just a resistive load. And in that case we will see how the filtering operation will be just made by the load directly. And that's all for today's video, and I'll see you in the next one.